Hi folks, welcome back to Physics with Captain Rod. Making this video here to describe Newton's law for rotation and how it relates to angular momentum. So what we're looking at, we've got this object here, some sort of generic object or body. Imagine it's free to rotate about this pink axis here, which is, you have to imagine the axis coming right at you. And for the sake of discussion here, let's imagine that this thing is restricted to motion in this plane here. All right, imagine a single force vector applied as shown to this object. Now, because this force vector is off axis here by some distance, this force vector is going to create a torque about this point. The torque is equal to the force times the perpendicular distance to the line of action. So again, remember, this force has what's called a line of action to it. I'll offset that just a tiny little bit. So the line of action for that force looks like this in green. The perpendicular distance to the line of action maybe is something like this. I'm going to draw this in red. All right, so this is the distance that is perpendicular to the line of action for this force vector. So the torque created, again, this is the Greek letter tau, which represents torque in most books I've ever seen, is equal to this force, whoops, and I'm just going to do this in kind of a scalar sense, times this distance. And again, if I wanted to draw this or do this in the definition by using the vector definition of torque, this would be the position vector crossed with the force vector. Either one of these are good enough for this discussion. So this expression, force times r perpendicular, gives the net torque acting on the system. Now, if this force remains constant, this angular velocity is going to start changing. And if the force stays constant, then the torque would be constant. And if I were to graph angular velocity against time, I'd get a linear type of curve. And again, I'm assuming it has started from rest. The slope of this line is an acceleration. The slope of that line is what I call the angular acceleration, or not just me, but everybody calls it that. And the angular acceleration is the rate that the angular velocity changes, which in an algebraic sense would be change in angular velocity over change in time, meaning if I pick any 2 points on this curve here, this would be the change in angular velocity, this would be the change in time. Or in the language of calculus and derivatives, it would be the derivative of the angular velocity. Pardon me for a moment. Okay, I'm back, so sorry about that. Got to kind of remember where I was here. This force times perpendicular distance gives the net torque. That's going to make this angular velocity change. So graphically, that might give a graph looking something like this. The rate that the angular velocity changes is called your angular acceleration. It's equal to change in angular velocity over change in time. Or in the language of calculus, it's a d omega dt. Right, Newton's second law for rotation is the sum of all torques, or I'm just going to say the net torque, is equal to I alpha. And again, if you're unfamiliar with that, just go back and look at my video about Newton's second law for rotation. Now, the alpha, again, can be written change in angular velocity over change in time. And again, I could also write this in the language of derivatives, the time derivative of the angular velocity dt. And this is a separable type of equation here. If I take a look at this, net torque equals I change in angular velocity over change in time. If I multiply both sides by delta t, this is now going to read your net torque times delta t equals, and what I'm left with is this quantity, I times the angular velocity. Now, I'm sorry, not angular velocity, change in angular velocity, which I'm going to go ahead and write final angular velocity minus initial angular velocity. Oops. Now, the I times the initial angular velocity is the initial angular momentum of the system. I times the final angular velocity is the final angular momentum of the system. So it's pretty easy to kind of rearrange this equation. I just want a little more room here, maybe shrink that down a little. It's pretty easy to rearrange this equation so that it kind of takes this form. If I take this product and put it on the left, it says I omega initial plus this torque net torque times delta t equals I omega final. This equation is saying whatever my initial angular momentum is, plus any torque times delta t, that's equal to my final angular momentum. Oh, I gotta sneeze. Okay. This thing right here, torque times time, is what's called an angular impulse or rotational impulse. It's a very handy, easy equation to use. It's particularly useful with certain types of impacts. There's lots of types of impacts where there might be a net force on a system, but not a net torque. If there's no net torque acting on a system during an impact, then this and this are equal, meaning that the initial angular momentum is equal to the final angular momentum. So again, this video is just kind of meant to be an introduction to this idea of rotational impulse and angular momentum. And again, a very important thing occurs if you're looking at a system and it undergoes some sort of set of changes via forces or whatnot. If there is no net torque acting on the system, then the initial and final angular momentums are equal. I think I'll save the examples of that for another video. Have a great day.